Hello, everybody. It's very hard to compete with this talk that we just heard. So first of all, I'm Tomer Shenar. I just started as assistant professor at the Tel Aviv University in Israel. I'm visiting here. Elia Mandel, mostly in this group. Elia Mandel. I'm sorry. And I work mainly on massive stars. I'm actually an observer. I'm not a theorist. So I hope you can still accept me here. And the question that I would like to address with this talk is something that concerns quite a lot of people, which is whether stars collapse into black holes. When stars collapse into black holes, whether they explode as supernovae. This is a very fundamental question, keeping both theorists busy. People trying to understand how stars collapse, whether they explode, but also it really affects rates of gravitational waves, the types of transients that we observe and stuff like that. So it's a pretty fundamental question. So one of the ways to get an empirical insight on this question is to actually find black holes in binaries, as I will demonstrate. And the question is, why should we even expect black holes to be in binary systems, like with stars next to them? So in the massive star regime, and when I say massive stars, I mean stars more massive than about 8 times the mass of the sun, stars that eventually undergo core collapse. We know that they are very commonly in binary systems. So more than 70% of the massive stars are probably born in relatively close binary systems. They undergo such evolutionary channels, right? They start as 2 stars, then evolve and go through different phases. And if one of the massive stars will collapse into a black hole, you will get a binary of a massive star and a black hole. So it's a natural product of binary evolution. And if you're crunching the numbers, recent estimates are something like 2% of the massive stars may have a black hole companion. For the lower mass regime, it's much less certain. So stars like our sun may also have black hole companions, but empirically, we think it's a very rare phenomenon, maybe 1 to a million, maybe even 1 to 10 million, or even less of stars like our suns have black hole companions. So I'm going to focus on the massive star regime, also because that's the most insightful one for studying what I just told you, whether or not stars explode when they collapse to black holes. So how do we even find these black holes? The majority of black holes were found in what is called an X-ray binary. So you have a black hole accreting from a nearby star, developing these accretion disks, which emit very powerfully in X-rays. We know quite a few of them. The problem is that in this case, the black hole and the star are so close to each other that you have very strong tidal interaction, circularization, mass transfer, and other effects that basically erase the history or the conditions that existed when the black hole formed. So it's a bit harder to understand how the black hole formed in such X-ray binaries. Another way to find black holes is actually a very exciting population. Probably something like 100 million black holes exist in our Milky Way galaxy, roaming about. They're called dormant black holes. They're just flying around space. The way to find them is with microlensing. So you see black holes going in front of a distant luminous source. So far, we only found one using the microlensing experiment that everyone kind of agrees on. But even if you find one, it's hard to understand how they formed, right? They just float in space. How do I know whether the star that formed them collapsed or not? Or maybe they're even primordial black holes. It's hard to tell. So the key is really to find such black holes in systems with stars, but that are not too close to appear as X-ray binaries, not too close to strongly interact tidally and so on. And these are called dormant black holes in binaries. We know of 5, as I will conclude with this, and we expect maybe something like 1 million binaries to exist in our Milky Way galaxy of this type. So how do we go about and find such systems? Just like planets, we want to look for the luminous star moving back and forth. And we can do that in 2 main ways. One way is to look at the sky and look at stars that are wobbling with astrometry. And the Gaia mission is probably most famous for that. And it has been to a certain extent successful, but so far less successful than we had hoped. There were some predictions that we might find like hundreds of such black holes. So far, only 2 were found with the Gaia mission. The other method is with spectroscopy. So we can see the stars moving back and forth in radial velocity space. And that's what I'm going to focus on now. Spectroscopy has the advantage that you can also do it in other galaxies. You're not limited to the nearby universe where you can still see the stars wobble. So in spectroscopic space, you would see your star moving back and forth in radial velocity. And here we distinguish between double-line spectroscopic binaries, and this is an example. You see here a spectral feature, which is splitting into two components as you take more and more spectra, and these are two stars that are moving back and forth. This is not where we're going to find our black hole. But some of these binaries also only show one spectral line moving back and forth, and you don't readily see the companion. So it's possible that the companion is there. It's actually more likely that the companion is there. It's a luminous star, and you don't see it because it's too faint. But it's also possible that it might be a black hole. So these are the systems that you want to be looking for, single-line spectroscopic binaries. So what can we do? Once you have a single-line spectroscopic binary, how can you know if it might contain a black hole? So first thing, kind of astronomy 101, if you measure the velocity of the star that is moving and you have an estimate for its mass, you can, from Keplerian dynamics, estimate or actually calculate how massive does the companion have to be, a minimum mass. You get a minimum mass from this. So let's say we know that the companion has a minimum mass of 5 solar masses. The question is, could we detect something, that signature in the spectra? So one useful technique to approach this is called spectral disentangling. It basically takes all these spectra, combines them together in such a way, or rather, if you want to think about it like this, it's a mathematical algorithm that separates these complicated spectra into two signatures that might be hiding in there. Originally, it was developed for double-line spectroscopic binaries to separate the two spectra. But actually, by using all the spectra together, you boost the signal to noise by the square root of the number of observations. And so you can detect things that are significantly fainter than what you would observe in an individual observation. And you can also use this method to measure the orbital parameters of the system. And so I'll show you now one example. Before I show you one example, I want to note that this technique was very useful to kill some quite famous black holes that were claimed to exist. One of them was claimed to have 70 solar masses in our Milky Way galaxy, and another one was claimed to be the closest black hole. And they all turned out to be these really unique binaries that contain two luminous stars. And we now call them black hole imposters. Okay, so there were quite a lot of people involved in these studies, and it's a really kind of an emerging field now. So that's a cool thing. So you should be wary when you hear about black holes. It's a rare thing, and people are really trying to look for them. I want to show you one successful, or so far, let's say, it hasn't been killed, example of a black hole that we found in the Large Magellanic Cloud. So how did we find that? I won't go into the details of the survey, but we ended up filtering a population of about 1,000 massive stars into 51 single-line spectroscopic binaries. Okay, so you just see one star moving back and forth. On the x-axis, you have the period of the binary. So it's going all the way from days to years. This is logarithmic scale. And on the y-axis, you see the estimated mass of the companion. Okay, so this is looks like a pretty massive companion. This looks like a pretty low mass companion. And the question is, where are the black holes? So what we did is we implemented spectral disentangling. And the results are, I'm just jumping straight to the results. Everywhere where you see a green star, this is where we find a luminous source. So we actually detect a non-degenerate companion in the system. This means that all of these cannot host black holes. And you remain with a few stars where you see the yellow circles, which is a weird symbols, but that's how it is. Yellow circles mean we didn't find any companion. And a few of them have black holes inside, and that's because they're quite good candidates because they have relatively high masses, and we couldn't find a luminous star. And one of them is so massive that we can prove using simulations that we would have seen something else. If we had a star the way it's 10 solar masses, in the paper we go all the way down to 5 solar masses or so, we're very conservative, we should have seen something in there. So this is the way we went about to claim that this system must host a black hole. So I'm just going to give you this example as how much it teaches us. This is a system that has a period of about 10 days. Its eccentricity is almost perfectly zero. It's very, very close to zero. So it's almost perfectly circular. And these are the masses, 25 solar mass star bound to a 10 solar mass black hole, roughly. Now, what can you learn from this? We know that these are used to be two massive stars. This guy collapsed into a black hole. If there was any explosion involved in this collapse, you have a very elegant formula, even if you ignore kicks and stuff like that can happen. You have a very elegant formula that tells you if a certain mass was lost from the system, it should induce an eccentricity, by this cute little formula. if you use this formula, you conclude that not more than 0.6 solar masses could have been lost from the system. In other words, it seems like hardly any mass was lost. If you do this work a bit more accurately, which my colleague Alejandro Viña-Gomez has done, and he's been here in the past, so some of you might know him, you can account for kicks and stuff like that, and basically you conclude a similar thing. In fact, it seems like the mass that was lost from the system is consistent with neutrino emission only. So it seems like the entire star simply collapsed into a black hole. And it's one of the first times we have direct evidence for such a process. We found on the same time a similar system, but in the Milky Way, which is eccentric. It seems that the black hole there did explode. I won't have time to go in detail into this system. So it seems that we do have some diversity in this black hole population, as is indeed predicted from models. I will just leave this as a final slide. This is the final census of the dormant black holes that we currently have. 3 of them are bound to solar type systems, solar type stars, sorry, and they are harder to interpret because they were probably formed from captures. And so we cannot use the same arguments I just used for low mass stars. For the massive star regime, we only have 2 so far, which I briefly introduced. So with this, I end. Thank you very much.
How much of an issue is the degeneracy of inclination? Because when you're looking at these single line spectra, like binaries, right? Obviously, the velocity is along that you're measuring is along the line of sight.
Yeah. So this is why you get a minimum mass. When I say minimum mass, it includes within it the inclination uncertainty. So as the lower the inclination, the mass only explodes. Yeah. And so
But your error bars on DFTS are very, very small. Right.
They're not that small. It was logarithmic. You mean these ones?
Right.
So, okay. So this is, you would have a probability distribution for the mass, given the inclination, given the uncertainties of the mass and everything. It's not a Gaussian. It's a funny thing that explodes to high masses. And this is the 68% credible intervals. Whether it's very small, I don't know. The minimum mass is 80.7 plus minus 0.5. So it mostly explodes towards higher masses, yeah.
Thanks. So, is the idea that, like with these binaries, would you expect them to be non-interacting during the evolution as well? No, so they would be interacting. Okay, yeah, because I was wondering because black hole mass is that quite small. So you assume that everything collapsed and it was not interacting, then you would expect more masses to explode soon.
So the process can be from the black hole mass alone, I wouldn't even say that's clear because before this star was a black hole, it was probably a Wolf-Rayet star.
Yeah.
They lose a lot of mass and they can actually end their lives with such masses.